Section 7.3, solving quadratic equations by graphing. So we're going to explore here. Graph the quadratic equation y equals x squared plus 5. So I go to my graphing calculator, whether that be on the internet, like Desmos graphing calculator, or maybe you have your own graphing calculator, an app on your iPad. And I go y equals x. If you're using Desmos, if you want to do x squared, you have a couple choices. You can do this A to the B button, or I just use Shift 6 to get that little hat. So it was x squared, and now I forgot my equation. Y equals x squared plus 5. And there I get a parabola. Okay, so and on here I can zoom in and out. I use the scroll on my mouse. You can also use these things here. So you can see I have a vertex at 0, 5. Its axis of symmetry is x equals 5. So now what it's saying is, how can I use this graph to solve the equation 21 equals x squared plus 5? So I want to know what x is to get 21. And it looks like there is two answers. It looks like x could be 4, and it looks like x could be negative 4. Okay? Another way I could solve this is I could say, well, y equals 21. And I could actually look for the intersection. And for some reason I have to press help, but you can see y equals 21 when x equals 4. And then I can come over here and I can see it also equals 21 when x equals negative 4. So that's how I can solve it. Then it says, what other equations could I solve? Well, when does y equal 20? Okay, so that I could see the 2 points where y equals 20. It looks like it happens twice. Or when y equals 5. Well, that looks like there's only one intersection. Okay, so that's how we can graph. And there's many ways that we can graph. I don't know why my screen's looking funny there. There's many ways we can graph. We can use technology. We could use a table of values. But what's important is that you understand we're looking for intercepts. Okay. Okay, I want to talk a little bit about what it means to solve an equation. If somebody asked me to solve y equals x squared minus 9, someone asked me for what the solutions were, or what the roots were, or what the zeros were, what they were asking for is they're asking for the value of x that makes the function, or that makes y 0. So it's as if we graphed, when does y equal 0? So we would have a straight line, and it's asking for this point right here and this point right there. That's what it means to find the roots, or to find the zeros. Okay, so in this case it would be x equals 3 and x equals negative 3. Okay, that's what it means to solve. So oftentimes in that last example where we wanted to know where it equals 21, we had x squared, and then we had, what was the rest of it? X squared plus 5 equals 21. So we actually graphed it, and then we graphed y equals 21. Let's see if we can get some graphing to go in here. My computer's being a little slow. So remember, we graphed that. Another alternative is we could have combined these two things. We could have said, we could have subtracted 21. Remember, we got the values of 4 and negative 4. Well, check this out. When we put it as x squared plus 5x minus 21, its roots are 4 and negative 4. So just another way to do this. We can either graph the left side of the equation and the right side of the equation on the same graph and get their intersections, or we can combine it and find the points where it crosses. Okay? So we're going to do a couple examples of that right here. We're going to go to this equation about building a kettle. Lamont runs a boarding kennel for dogs. He wants to construct a rectangular play space for the dogs using 40 meters of fence and an existing fence on the side of the space. Write a, write a function to describe the area. Well, area is length times width. Okay? But what we want is we want it only in terms of width. Okay? Well, if you think about it, width, let's let be W and W. The entire side is 40. So the length is going to be 40 minus this side W and that side W. So that's really what length equals. So we could rewrite this as 40 minus 2W, that's your length, times width. Expanding this, I could get area equals 40W minus 2W squared. Okay, so that's my expression. So now it says write equations you could use to determine the widths for the areas at 250, 200, and 150. And I'm going to start with 150. So I could write this as 150 equals 40W minus 2W squared. So going to solve this, I could graph y equals 150 and y equals 40W minus 2W squared, and I could look at their intersection. Or I could just graph y is equal to 40W minus 2W squared, and I could bring this 150 to the other side, minus 150. Okay, so let's see if we use those two strategies if we get the same answer. And let's hope that my graphing calculator starts working here. Okay, so I said I could graph y equals 150, and I could graph y equals 40W minus, oops, y equals 40W minus 2W squared. Okay, I'm probably going to have to do some zooming out because I'm at 150. I'm going to move down a little bit. Okay, we're getting close to 150. Okay, so there's y equals 150, and 40W minus 2W squared is still graphing. I'm going to press pause, and once my computer starts working, oh, there we go. Okay, so I want this intersection point, and let's see. So it looks like that happens at when x equals 5.1 and when x equals 14.4, 5.1 and 14.4. So I said this would be the same as if we just went y equals 40W minus 2W squared, and then if I subtracted 150. I said I could also use this strategy. Whoops, I have to graph correctly. Minus 150. If I graphed this correctly, I said this would be the same as my intercepts. So let's see where my green graph is going to come up. I'm going to pause and hopefully. Okay, so it looks like it wasn't snapping very well. If I follow this, it equals 150 at 5 and at, see if I can get this, and 15. So now what I'm saying is my green graph, its y-intercepts should also, sorry, its x-intercepts should also be 5 and 15. So we're looking at the x-intercepts of this graph, and look, it crosses it at 5, and it also crosses at 15. Okay, so two ways to solve there. There's lots of great examples. We could look at a couple other widths, but we're only going to look at some because you know what? This is all in your textbook. So just to summarize what we learned, a quadratic equation can be solved by graphing the corresponding quadratic function. The standard form is ax squared plus bx plus c equals 0. The roots are the x-intercepts of the graph and the corresponding quadratic function. These are also the zeros. So roots, zeros, same thing. A quadratic equation is a second degree, so we have x squared, that contains a polynomial in one variable. If a quadratic equation is in standard form, so if you bring everything to one side, we graph it and determine the zeros. We determine the x-intercept. We looked where it crossed the x-axis. If it's not in standard form, you can graph the expression on the left side and graph the expression on the right side on the same axes. So that's where we graphed, in this one, that's when we graphed 150, the left side and the right side, and then we looked for its intersection, and that's what it'll say next here. The x-coordinates of the point of intersection are the roots. For any quadratic equation, there can be 0, 1, or 2 real roots. This is because a parabola can intersect the x-axis at 0, 1, or 2 places. So what that means is we can have a parabola and it cannot intersect ever. It can intersect exactly only once, or it could intersect at 2 places. Okay, so that's how you can have 0, 1, or 2